In this video, we are going to derive the electric potential for a point charge. So what we're looking for is a generic equation that we can use to find the electric potential in the vicinity of some point charge. So the first thing that we need to do is that we need to realize that if I move within the vicinity of some point charge, that my electric field is changing. And so I can't use my formula for electric potential that I was using when my electric field was constant. So previously we've used the equation that the change in potential, delta V, equals negative of the electric field dotted with the displacement. Now, this is fine as long as your electric field is constant, but if the electric field varies over the distance, then we need to use a new equation, which is that the change in electric potential equals the negative integral of the electric field dotted with the displacement. So here I'm writing dl as the kind of describing the path that we take. And to motivate why this is true and why we need to use this equation, let's consider moving between points A and B in the electric field of some positive point charge plus Q. So the first thing that we can do is we can note that the electric field at points A and B is different. So of course at A we have some electric field E sub A, which looks like KQ over R sub A squared R hat. R hat indicates that it points radially outward. We also have an electric field at point B, which has a different value of KQ over R sub B squared. Also R hat points radially away from the charge again. Now, if you wanted to use our top equation, negative E dot D, the question that you would need to say is, if you want to move from point A to point B, you have some displacement vector that you could draw, right, which points from A to B. So you have your D vector, right, which I can draw in here. So this would be your kind of trial D vector if you wanted to use our top equation. But the question is, which electric field would you dot this D vector with? Would you use E sub A? Would you use E sub B? Would you use some value in between? And the answer is that none of those things really work, because if you used E sub A, then you would be assuming that the electric field has the same strength as E sub A for the entire journey from A to B. But that's not true. It changes, right? The same as if you used E sub B. So we can't just pick one electric field value and try to use our top equation. So this equation fails, at least we can say, based on the fact that there's no electric field, there's no one electric field that we could use to use that equation. Now, in order to solve this, what we can do is we can actually break our journey up into little displacements. So imagine that I try to move from A to B, and I take some little displacement dl vector. And I could write this as dl magnitude, the length of my vector, multiplied by r hat. It points radially away from the point charge, so it should have a direction of r hat, and it has some tiny length dl, right? And I'll call this dl1 because it's the first step in our journey, right? Now, we could write our change in potential as we move along this dl vector as delta V sub 1 equals negative E sub 1 times dotted with dl sub 1, right? And we can assume here that our distance traveled is small enough that we can, in fact, assume that the electric field is constant. So we assume that dl, my tiny displacement, is small enough that E is effectively constant along dl. And so I can use my standard equation. I moved just a very small bit and I get it. I can use my constant electric field equation. But I haven't made it all the way to B, right? So I'd better take another step. So now I can go from the end of dl1. I can take another little step. I'll call it dl2, which has some length dl2 and some direction r hat. And again, I could make the argument that I'm making dl2 small enough that the electric field is effectively constant, and I could write some delta v2 as negative e2 dot dl2. And hopefully you can kind of see where this is going. I can just keep adding on little displacements, which hypothetically should all be the same length, but it's not. I'm not going to worry about my artistic integrity right now. You add up a bunch of little lengths. And what you can end up doing once you've done this is you can write your total change in potential as a sum of all of these little steps. So I can write delta V total looks like delta V1 plus delta V2 plus 3 plus 4, etc., right? And I could write this as the sum from, say, I equals 1 to infinity of all of my delta V's, right? And the infinity comes from the fact that our goal should be to make dl infinitely small, such that our assumption that E is effectively constant becomes actually true. If I make dl infinitely small, right, then E is actually constant over an infinitely small distance, right? And so you can turn this sum into an integral. So then you can say this looks like the sum from infinity of negative EI dot DLI, where I is standing in for 1, 2, 3, 4, etc. And when we make DL infinitely small, this becomes the integral from my starting location to my finishing location of negative E dot DL, which is exactly what we wrote in the beginning. We said that we needed to write our change in potential as an integral of all of these things, and I wrote it slightly differently. I moved the minus sign out front. So I said it equals integral, and our starting position is A, our ending position is B of E dot DL. Now that we have our equation for the change in potential in a changing electric field, let's try to find the electric potential for a point charge. So imagine that we move from some radius A, r sub A, to some point B, which is infinitely far away from our point charge. In this case, we can consider our dl to be little steps again in the r direction. So I'll write it as dr r hat. And we can once again write our electric field as kq over r squared r hat. This leads us to the equation of E dot dl equals kq over r squared dr. So now we can actually take this integral. That is that the change in potential is the negative integral from point A to point B, which I'm going to write, because we are dealing with r's, I'm going to write this as from our initial radius RA to our final radius r sub B, since the variable that we are integrating over is in fact the radius r. So we can write this as kq over r squared dr. The k and the q can get pulled out front, so we can write this as negative kq integral from RA to RB of dr over r squared. And this then becomes negative kq times 1 over r negative from RA to RB. And we can now cancel out the negatives and write this as kq over r evaluated from RA to RB. Now, RB is infinity. So when we write this, our delta V here, this looks like KQ over infinity minus KQ over R sub A. Anything divided by infinity is going to be 0. So we can simply write this as the change in potential is negative KQ divided by R sub A. Now, it makes sense that we would find a negative value because we moved with the electric field. So when we move with the electric field, we lose electric potential. Now, we can reverse this and imagine going from B to A. So I'll specifically write my subscript from A to B here for my electric potential. But we can imagine reversing this and going from B to A. That is the change in potential starting at infinitely far away and going to some point at a distance R sub A is going to be equal to positive KQ over RA. Because if we lose potential going in one direction, we must gain it moving in the other direction. And more generically, we just say that the potential, so we don't use delta V here for point charges. We actually just write the absolute potential of a point charge as being KQ over R, where it is implied that this is measured relative to the potential at 0, the potential at infinitely far away, which is equal to 0. So whenever we say the potential of a point charge, we write it down as kq over r, where we are always referencing the fact that being infinitely far away from the charge is where we assign potential to be 0. Note that if we have a positive charge, that the potential of that charge is positive. If we have a negative charge, the potential of that charge is negative. As a quick check on how we can use this equation, let's actually put in some numbers. So let's imagine that we have some positive charge of 3 microcoulombs. And we want to find out the electric potential at some point here, which is a distance of 0.12 meters away. We can write the absolute potential, electric potential, at that spot as K times 3 microcoulombs divided by 0.12 meters, which turns out to be 2.25 times 10 to the 5th joules per coulomb or volts. Now imagine that we wanted to bring in a charge and actually place it there. So we have some charge. Let's say that the charge is a 5 microcoulomb charge. It's initially infinitely far away, and we bring it in and we place it at this point. I'll call the point P. So this is the electric potential at P, and we could figure out the potential energy of this system when this 5 coulomb charge is brought in and placed at P. That is going to be equal to the charge that is moved, which is my 5 coulomb charge, multiplied by the potential at that point P, which is going to be 5 microcoulombs multiplied by my 2.25 times 10 to the 5th volts, which is 1.12 joules of energy stored in this system. It makes sense that this potential energy should be positive because we had to do work in order to get that 5 microcoulomb charge there. These two positive charges don't want to be together. If we let them go, they will repel each other strongly. And so it makes sense that this system is storing positive potential energy. Now, if instead we brought in a -7 microcoulomb charge and put it at the same spot, then the potential energy of that system, so now the 5 microcoulomb charge is no longer there. Still, I just have the 3 microcoulomb, but I'm bringing in a different charge and placing it at point P. And the potential energy of this would be, again, Q, but now my Q is my charge that I'm bringing in, -7 microcoulombs, multiplied by the voltage at that point, which is going to be -7 microcoulombs multiplied by 2.25 times 10 to the 5th volts. And that value is -1.57 joules. Now, it also makes sense that this system should have negative potential energy. That's because the electric field did positive work as it pulled these two oppositely charged particles together. When the electric field is doing positive work, you are losing potential energy. You can also think about it as the fact that in order to get these two particles apart, it would take a lot of work from you. You would have to pull on these two particles in order to get them apart because they are attracting one another, the negative and the positive. So this is just an example of how we can physically calculate the electric potential at some location near a point charge, and then find how much potential energy would be stored if another charge ended up there. Finally, I just want to note that the electric potential of the point charge depends only on the distance that you are from that point charge. So the idea is that you can create what's called equipotential lines. So if I imagine that I have some positive point charge, the electric potential depends only on how far I am from the charge. Moving left or right doesn't change my radius. So if you imagine that I start here, we know from previous lectures that you can move perpendicular to an electric field line with no change in potential. If we move perpendicular to electric field lines, we can move without changing our electric potential. It's only when we move parallel to the field lines that our electric potential changes. So we could plot out a path where we are constantly moving perpendicular to the electric field lines. And if I draw this out, that path looks like a poorly drawn circle. It should look like a well-drawn circle. But what you'll notice is that every time I cross a field line, so I'll highlight it here in blue, every time I cross a field line, I am perpendicular to that field line. So if I move along this red circle, my potential, my electric potential, does not change. This is called an equipotential line. And you can move there without changing your electric potential. And if you are a charged particle, you can move around that line without actually changing your potential energy at all. And this is a little bit misleading because I'm drawing it in 2 dimensions, but really there is a spherical shell surrounding the point charge at a constant radius. So I can try to draw it like this, and there's something on the back here, right? Anytime that you are some fixed radius from that charge, you are on an equipotential surface, right? So as long as I stay a distance of, I'll call this just big R, as if I start at big R and I stay a distance big R from my central charge, I can move anywhere I want without changing my electric potential, because my potential is just KQ over R, my radius. My radius doesn't change, my potential doesn't change. And this is not unique to the radius that I chose. There are equipotential lines at every radius. So I could draw another equipotential line close to my charge. So here is another one. It is another poorly drawn circle around the charge at some radius that I'll call D, right? So that is a different equipotential line. It's at a different potential than my red sphere, but everywhere on the blue sphere that I just drew is at some other potential. And I can move around that surface without changing my electric potential. So the takeaway from this is, if you're ever asked to find the electric potential at some point relative to a point charge, the only thing you care about is the charge of that point charge and the distance that you are from it. The angle that you are, your relative position in kind of space, doesn't matter. Only your radial distance from the point charge sets your potential.